Illustration number 12. We have to prove in this case the energy density associated with the magnetic field of a very long solenoid is V square upon 2 mu 0. So first of all I start with the magnetic induction of a solenoid. That is given by B is equals to mu 0 Ni divided by small l, where N is the total number of turns of solenoid. Mu 0 is the permeability of free space. I is the electric current passing through solenoid. And L, that is the length of the solenoid. So with the help of this, I am consider over here that if the self-inductance of the solenoid is capital L, then the energy which is stored in the inductor, that means U, potential energy, is given by 1 by 2 Li square. The above equation I am considering as equation number 1. So, substitute the value of equation number 1 into equation number 2. Therefore, U is equals to 1 by 2 L into, if we further reduce equation number 1 for object I and squaring it, then we will get this value B square L square upon mu 0 square N square. But the self-inductance of a solenoid is given by that means L is given by mu 0 N square into A divided by L. Here one new quantity is coming, that is A, which is the area of solenoid. Therefore, substituting the value of L, so 1/2 is as it is. Instead of L, mu 0 N square A over L into B square L square divided by mu 0 square N square. So here N square is cancelled out. Here mu 0 is remaining in the denominator. L is also cancelled out. So the final answer for potential energy U stored in the inductor is 1 by 2 AL B square upon mu 0. So, the energy density is given by the energy per unit volume of solenoid. Here we have considered volume instead of area because of the shape of solenoid. So, the density I am considered over here as rho and is given by the energy per volume. Here volume is area into length and the value of U is 1 upon 2 mu 0 AL B square divided by A into L. So the remaining terms are B square upon 2 mu 0. So that was our task and that has been performed. So we have proved that the energy density associated with the magnetic field. So here I am putting the subscript B. So that will suggest the energy density with magnetic field of a long solenoid is given by this equation. So with this now our theory part is over. Now we will switch on to one application of electromagnetic induction, that is of AC generator. So let's start the last example of this chapter number 1, illustration number 13. The number of turns in the coil of an AC generator are 50. Therefore, capital N is equals to 50 and its cross-sectional area is 2.5 meters square. Therefore, A is equals to 2.5 meters square. This coil is revolving in a uniform magnetic field of strength 0.3. So here B is equals to 0.3. Here the unit is not written, but you have to understand the unit of magnetic field strength is Tesla. Now, it is moving with a uniform angular velocity, means omega is also given to you 60 radian per second. And the resistance of the circuit comprising the coil is 500 ohms. So here R is also given to us 500 ohm. So first we have to find out the maximum induced EMF. So we have to find. So Vm actually. So starting in this way, the induced EMF generated in an AC generator is given by V is equals to Vm sin omega t. But if you remember, we have assumed this Vm at a particular mixture of three quantities, that was NBA omega sin omega t. Therefore, the maximum induced EMF is given by NBA omega. We have all these values. N is equals to 50, B is 0.3 Tesla, A is 2.5 and omega is 60. So the final answer will be 2250 watt and If you write down in more simplified way, then you can also write this equation as 2.25 kilowatt. So this is the maximum induced EMF generated in the AC generator. Now the second task is calculate the flux passing through the coil when current is 0. So here we have to assume the current is 0. So according to Ohm's law, when current is 0, then voltage will be also 0. And here we have the equation of voltage or induced EMF as minus d phi by dt. So that will be also 0. And what it means? It means that the value of phi will be constant. And if it is constant, then I can consider its value directly as BAN, and hence the value of B is 0.3, the value of A is 2.5, and the number of turns are 50. So the value of phi is 37.5 Weber, and hence this is the value of magnetic flux which is passing through the coil. Now the third task which is given to us is also to find out the flux, but here the condition has been changed. Here the condition is given that the current is maximum. So when the current is maximum, voltage V will also be maximum. And we know according to the graph of V versus omega t, whenever the value of sine omega t is equals to 1, or we can say omega t is equals to pi by 2, the value of V was 1 or is equals to Vm. So V is equals to NBA omega cos, here sine will become, so I am writing over here sine omega t. So the condition for maximum current is sine omega t is equals to 1, and therefore omega t should be of pi by 2. Now according to the equation of the magnetic flux passes through the coil, is given by phi is equals to BAN cos omega t, that is equals to BAN cos pi by 2. But here we can directly say the value is 0. So when the current is maximum, the flux will become 0, and this relation we have also determined in the graph. Whenever the current was maximum, or we can say omega t is equals to pi by 2, the value of pi was 0 and the value of voltage, or we can say the induced EMF, was maximum, that means up to Vm. So with this our chapter number 1 is over.